This is a very chill, low-key first lecture, as usual. Like, I'm not going to talk about anything deep. It's mostly just the introduction about, this course and some of the materials that we're going to cover, some of the topics we're going to cover, and a very, very high-level introduction of machine learning. Still from a somewhat traditional viewpoint. So the teaching staff, this is me and Chris. I guess Chris is not here today, but he will start to teach from the next lecture. So basically, either me or Chris will come to the lecture to give the lecture. I guess you can look him up. I don't necessarily have to introduce him that much. He probably have an introduction for himself, but he works on a lot on like all kind of like AI large language models, efficiency, database, everything. So, and I, in my PhD, I worked a lot on theory for deep learning, and over the years, I started to work on more empirical stuff. These days, I'm working on AI for sciences, AI for math, like self-improving algorithms, so on and so forth. Basically, like training large language models. So prerequisites, right? So I think, as usual, we require some background in probability and linear algebra, and these are some of the CS229 or CS216. This list of like courses might be a little out of date. There are maybe equivalent courses, on campus, which I'm not aware of. But generally speaking, you need to understand some of these buzzwords a little bit. If you don't know them, you can go to the, there's some kind of like there's something called section. There's something called, Friday TA lectures. So those are for some of the backgrounds that you may that you can learn there. So but generally speaking, if you don't know anything about this, you probably should take this course later. But if you are just missing some aspects, then you can come to some of these Friday lectures to catch up with some of the basics. Yeah, and I think one highlight I would say is that it's still a pretty mathematically intense course. We are trying to teach the basics, in some sense the foundation of machine learning, not necessarily proving theorems, but just there are derivations, mathematical kind of like derivations, mathematical modeling formulations. We focus more on those as opposed to programming. So we try to understand the basics behind the algorithms and the code. So, so probability and linear algebra are pretty important, for understanding some of this. Yeah. So, AI tools policy, which is, increasingly important these days. I use AI tools every day. So we do allow you to use tools, but, there are some restrictions. For example, you cannot copy the results from the tools to your submission, right? So in some sense, you can just only use them as a human collaborator, as if they are human collaborator or maybe superhuman collaborator, but not like let them generate codes that directly go into your questions. So there are a lot more details on the website, and we're happy to clarify if there are any questions. So these rules probably sounds a little bit restrictive, to some degree, but I think this is in some sense, what's the right word? Like to encourage you or to enforce the learning, like the updates of your brain. Where if you're just training if you're building an agent that the agent understands the materials, then you probably don't have to take this course, right? So this is not about training your own agent. It is about training yourself, like your synapses. So, at least that's my interpretation so far. But we are still taking a somewhat kind of like, relatively traditional approach to think about machine learning, which I think still applies because, I think in terms of, in my probably biased view, I think the methodology of training the models are still very similar to the old days. But the way we are using the models are very different. So for example, in the old days, I think, if you use the machine learning in a company, you have to get complicated kind of like pipelines, get the data, train the model, so on and so forth. But now you just prompt, you just ask questions directly, you build some kind of like skills in cloud code, so on and so forth. Right. So, I think we are probably not going to focus too much on using these models. We are not going to teach that much about how to use cloud code work, or cloud code to write code. But we are more focusing on how to train, what's the fundamental technology to train these models. So that's why I think most of the existing context still apply. We did drop some of the outdated stuff. So, and when I was reviewing this, some of these lectures, just last week, I found surprisingly some of these definitions still kind of holds. This is 1959. It's basically ages ago for machine learning. But somehow the definition still seems to be pretty much the right thing. Machine learning is a field of study that gives computer the ability to learn without being explicitly programmed. I think at that time, explicit programmed means that you program some kind of like code to play chess. And that's what explicit program means. And learning means that you somehow use some data and you train some model to predict or to make the decisions on what moves you should make. And then in 1998, that's like 28 years ago. So, Tom Mitchell, he's a professor at CMU. He said that, a computer program is said to learn from experiences E with respect to some class of tasks T and performance measure P if its performance at tasks T as measured by P improves with the experience E. I think there's probably a small typo there. Anyway, so, I think this definition is very interesting because it mentions a few important components here, or concepts here, right? One is experiences. This is kind of like a different way to say data, right? And these days experiences is even more broad, right? Because they are synthetic data you generate, right? They're in the thinking tokens. I'm not sure whether you're all familiar with that, but like the thinking tokens generated by the models, they are data from the web, they are data from the real world, they are human label data. All of these are kind of experiences. And tasks, in the old days, the tasks are very specific. You have like an image classification, you have like some kind of like price prediction problem, so on and so forth. Each of them is a task. These days, you still have tasks, the concept of tasks, but it's more general purpose. You can solve, like you have one model that can solve 1 million tasks. And there's performance measure P, which is also very important because this is the accuracy, so on and so forth. Because you do need a goal in some sense, to drive the learning of these models. And I think also, in the if clause, I think it's trying to emphasize that, this model seems to be better and better if you train it for longer and longer with more and more data, right? And that seems to be, that's a very important thing for learning, right? So if you have more data, it's not improving, then it's not learning, right? So I guess for games, experience is data, the performance metric is the winning rate, and the task is just a game. So, and so these are the broad definition. Let's try to kind of like break down a little bit, right? So if you have a taxonomy, I don't think there's a consensus on, what's the right taxonomy. I think the field is moving so fast so that there's no really consensus on anything because there's no even time to reach a consensus in some sense, right? Because sometimes you reach, at the moment you reach a consensus, the thing you are trying to have a consensus on no longer important, right? So because people have moved to different techniques. But these kind of things, at least, if you quote me on how do I classify machine learning techniques, nobody will find crazy. So I'm not saying this is a universal ground truth, but this is a reasonable view. So I think you have supervised learning, unsupervised learning, and reinforcement learning. Of course, they're intersecting. There are a lot of intersections and even more intersections these days. And also, you can think of this as tasks. You can also think of this as kind of like tools or methods, right? So especially these days, I think the tasks, I think people mostly think of this as probably methods, or paradigms, as opposed to the end goal, right? Because in some sense, nobody has the end goal of just doing supervised learning for one task, right? So like the end goal is always having general purpose, automatic learning kind of agents, so on and so forth, right? So, but supervised learning is still used, in building these agents, right? So, you probably heard of the word SFT, that's called supervised fine-tuning, which is one form of supervised learning. So, but they are more like tools, but not end goals. Anyway, but I'm going to introduce all of this a little bit on the high level. So I guess supervised learning. Maybe let's think about this. 15 years ago, if you study machine learning, this is probably one of the interesting applications, house price prediction. So given a data set that contains some examples, and you want to predict what's the price for the house. So basically, it's kind of like each example is one property, and you have like x-axis the square feet and y-axis the price. So given the square feet, you want to predict the price. And if this is the only thing you are given, then okay, I guess I'm going to introduce some mathematical notation which we're going to use throughout the lecture. Of course, we're going to remind you about the notation. So often x is used to denote inputs, y is used to denote output. So here square feet is the input, and price is the output. And you have many pairs of this because you have many properties, and each property is a point. And the question is just that if it has x square feet, what's the price? And when you test it, you just say I have an x, and I want to know what is the corresponding y. And as you can imagine, the simplest way is that you just fit some line, and then when you predict, you just say you read off the value of the line at the position of x is equal to 800. And in this case, probably fitting a square quadratic function is a bit better, then you get a different prediction. So, and in lecture 2 and 3, I think we're going to cover some of this, how to fit a linear or quadratic functions to a data set, and what are the training algorithms, what's the optimizers, what's the loss functions, and what's the algorithms, so on and so forth. So, of course, this is very simplistic because, it's not only about the square feet, you probably also need to know the loss size. Then you have a two-dimensional problem. Now you have x1, x2 as inputs, and you have y. And now if you visualize, you are in 3D settings. And just to clarify some of the notations or the kind of like the wording. So in machine learning, every concept has probably more than one name. Like there's so much confusions in the past. Now actually there are fewer confusions because some of these words are no longer used. In the old days, I think features and inputs are both referring to the values you are given, and the price is the output you want to predict. And also sometimes people call it labels. I think I just tend to use input and output these days to avoid kind of like the confusion. But sometimes people still use the word labeling, which means that you give a label or give a design output, you provide the output for certain input, right? You can have human labels, you can have machine labeling, so on and so forth. Okay, so and there's a concept between about the output type. So it's called regression versus classification. So if the output is a continuous variable as for example price, then it's called regression. So if the output is a discrete variable, for example a label, something like flamingo, or like what for example you can label the image with some kind of like a tags, right? So if the output is a tag, then it's a discrete concept, and then it's called labels. And the problem to assign labels to the input is called classification. So for example, if you are trying to know whether it's a house or townhouse, then that's two discrete variables. Then it's one discrete variable with two options. Then that's called classification. And if you have a classification problem, then you cannot visualize in the same way. So I think this is one of the ways to visualize. You have two-dimensional inputs, right? So lot size and square feet, and then you can label with like a triangle or circle, and you can see like the way to classify whether this is a house or townhouse is probably by building some kind of classifier that separates the plane into two parts, and you say everything above the line is a house and everything below the line is a townhouse. Something like that. And in lecture 3 to 5, we are talking about classification. And this is actually very important, even for these days, because all of these large language models fundamentally is a classification problem. When you're predicting the next text, next token, or the next word, the word is a discrete label. So it's just that you have a lot of labels. You have like 50K, these days probably 250K different words or tokens, and you are classifying into all of those discrete choices, right? Like you have to choose one next word among 50K possible options. And then you can talk about, even high-dimensional inputs, right? So like the inputs, eventually you want to know everything about this property to be able to predict the price. So you can have leaving size, lot size, floors, conditions, zip codes, so on and so forth. So eventually everything is a high dimensional problem. And also the outputs can be also high dimensional as well. Here I'm only having the price, but you can have even much more complicated outputs. So and some just, you can, as you can imagine, there are some kind of applications, image classification. So this is a classification problem because each image has a label, like, which is the main object in the image, flamingo, quack, quail, so on and so forth, Egyptian cat. And this is actually at the beginning of this AI era, right? So like basically, I think Fei, she's a professor at Stanford, so she and her team collected this 1 million this data set called ImageNet, which has 1 million image and label pairs. And 1 million pairs at that time is really big. The second largest data set was like 50K. It's like 20x bigger than the second biggest one. And then Jeff Hinton and Alex Krzyzewski and Leah Saskever, they published the famous AlexNet paper, which was trained on this data set, and with neural networks and gets fantastic performance. And that's pretty much the beginning of this era of AI. Of course, there are several waves in the last 10 years, right? There was like the vision, innovation, and then people moved to language. And then, at the beginning, the language models is of one form, and then later on we have the large language models, and that goes to, so basically that's how this last kind of 10 years has evolved. But everything started with this, this very, very big data set, so that you can do this very simple classification problem at this point, right? Like, in 2026, this is a problem that's supposed to be, it's one task, first of all, right? So, like, you can only do the only thing you can do with this is, like, you can label it, nothing else. You cannot ask any questions about these images, right? So, it's only 1 million pairs, right? And the accuracy is only, like, at that point, the first paper, I think I remember the accuracy was on 50%, and now it's like 95%, maybe 97%. Anyway, so the X is the raw pixels of the image, and Y is the main object, which is a discrete object. So, and then in vision, there was a few years people study, people actually still use these kind of tools to do bounding box localization. because each image is not only one object. You can locate every object and have bounding box for them. And in this case, the Y is the bounding boxes. The output is the bounding boxes. How do you describe the bounding boxes? You describe it by 4 numbers, 1 number for the left bottom corner, and two numbers for the left bottom corner. That's like X or Y coordinates, right, for the bottom left corner, and 2 numbers for the top right corner. And with these 2 corners, you uniquely identify the bounding box, right? So basically outputs are 4 numerical numbers, and the input is still the raw pixels. And machine translation is one of the supervised learning problems. So basically you just have the input, which is, English, the output it could be Chinese or any other languages or vice versa. And, so this is X to Y. I think by the way, in this course, we're not going to cover too much about applications. We are mostly trying to teach a little bit about the fundamental techniques behind these applications, and use more toy examples to demonstrate the techniques. If you really care about applications, I think there are other lectures or other courses on campus that are more useful. So, and deep learning, as I said, is one of is the technique that enables all of this. So basically, it's a neural network, which is very complicated. I'm showing small examples, but actually there are like millions of neurons or billions of neurons in it, and okay, maybe not billions of neurons, but like there are billions of parameters. Each parameter is actually like some kind of like edge. We're not going to details today, but so in some sense, this is kind of like simulating, to some degree, simulating the human brains, right? So the neurons are the nodes, and the edges are the synapses, and you give this image to it, and then it outputs the labels. And we're going to talk about the basics about this, like what's how do you define neural networks? What are some of the basics on how you define it, and what are the important things to pay attention to, and then most importantly, how do you train the models by computing the gradient? Because you're going to define loss functions, and then you do this so-called backpropagation, and this backpropagation is how you automatically compute the gradient of such a complex model or function, and that's lecture 7 and 8. So that's supervised learning. Let me see how much time I'm spending. Okay. Any questions? Feel free to interrupt me at any point. This is a very low-key lecture. I think I've only spent probably 15 minutes if there's no question. Yeah. Okay. Anyway, so let's move on to unsupervised learning. So what does that mean? So it means that you only have a data set with only inputs, but there's no outputs. So there's no clear tasks, right? Because you don't know what they are trying to predict. You just only have inputs. So, for example, for supervised case, you have the label, which is like house versus townhouse, right? So you have this triangle versus circle in the plot. But if you are unsupervised, then you don't have that information. You just have a bunch of like, data, right? And you don't know what the type of the house, it is. So it's just a bunch of points on the plot, and you still want to understand something about it, right? So there's still some patterns on the right-hand side figure, you can clearly see, if you're human, right? So in some sense, we are trying to get as much as possible from the data without the labels. That's pretty much what unsupervised learning is doing. It's a very vaguely defined, goal, because what does interesting structure means in data, right? What does that mean? In some sense, it actually depends on your methodology, right? Like different methods will give you different structures, right? In some sense. So, for example, for this data point, there's a technique called clustering, which just means that you find out, data points that are somewhat similar, right? And in 2D, it's actually pretty obvious. You just, I think if you ask humans to cluster, you probably get similar results. Or maybe you can cluster in this way as well. I guess this is probably better clustering because there's a clearer pattern. And in lecture 9 and 10, we're going to talk about some of these clustering algorithms, right? Like what's the way to design these algorithms, what's the loss function, or what's the objectives here, so on and so forth. So, and in terms of applications, I guess these are some of the classical applications, right? So, for example, this is about clustering genes, right? So, every column is the gene expression, the genes for one individual, and you have so many individuals that have different genes, and you put them into a table, and you can see if you sort them in the right way. This is actually somewhat sorted, so you can see clearly patterns, right? So there are a bunch of individuals which have those kind of genes, and there's a bunch of individuals which has these kind of genes, and then you can classify them into different types, and understand what genes can cause what kind of like disease or symptoms, so on and so forth. So and these are the clusters probably, and you can also cluster words or documents. So I think this example is like you have on the horizontal dimension is documents. So each document contains a number of words, and you count how many words. For example, this means that pollution show up in document D0 for a lot of times, and that's why it's darker. And you see this, so basically you count how many times each word shows up in the document. That's it. That's how you build this table. And you don't see much pattern here, right? But if you reorder them, and let me see whether you can see, oh, sorry. Let's wait for the animation. Okay, yeah, so after you sort in the right way, you can find groups of like documents which have similar patterns, right? For example, these 3 documents all have a lot of mentions of shuttle, space launch, and booster. That seems to be about, maybe SpaceX or something like that. And there's the top left kind of like corner is about air pollution. Environmental is about environments. So you can figure out similar words and also similar documents, right? Because these documents are similar and these documents are similar, so on and so forth. So, and this popular technique is called LSA. And we're going to talk about how to, do some of this in lecture 9. And then this is like a post-deep learning, era techniques. You can also, represent, words, by vectors. So basically every word you can encode it into a numerical vector, which is like sometimes 1,000-dimensional vectors, or sometimes even longer. And it turns out that actually these vectors not only have a lot of semantical meanings. First of all, like similar words can have similar vectors, right? So Rome, Paris, and Berlin, they have like vectors in the high-dimensional space that are very close. And also sometimes the directions can correspond to relationship. And for example, this direction from left to right corresponds to a relationship between the capital and the country. So basically, if you find Italy and you don't know what's the capital of it, you just go in this direction and find which point you hit, and that word you hit will likely be the capital of Italy. And the same thing for France and Germany. So you have one direction where you can use to search for the capital of the country. And there are many relationships like this people have found. And we're going to talk about how to kind of like learn this kind of embeddings or encodings of the natural language. And all of these are learned by training, in those days, they are 2014, 2015, right? So they are training on unlabeled data sets, basically Wikipedia. I think actually I got this image from the web. So the free I think this becomes the free corpus, right? Because people are using this to train models. Of course, these days Wiki is a very small corpus. It's like probably like 1% or like 0.1% of the total corpus and these days. So and then let's talk about we'll talk about large language models. I guess this is I think large language models also have like different kind of like nuances. We're going to talk about basically the general idea is that it's a general purpose model learned on unlabeled and massive data sets. And it's general purpose because it's not only for example, before here, what's the purpose here? You are trying to understand which words are similar to the other words. You understand the relationship, right? So here you are trying to understand the relationship between documents, the relationship between words, so on and so forth, right? So that's one task in some sense, or maybe two tasks. But here, when you have large language models, we have ChatGPT. It says, what's the agenda? What's on the agenda today? You can ask anything. I guess that's the what they have here, right? Ask anything, right? You can ask anything about, anything, right? So it's not only one task or two tasks. It's about general purpose models. And we're going to cover something about the architecture, like what neural networks you're going to use for this kind of like pre-trained large language models, and what is the loss functions people use to train these models. And then we're going to talk about some of the little more advanced things, like how do you prompt these models, or how do you train the models to be more responsive to prompting, right? So I guess when you use large language models, you probably have seen that it does depend on how you ask the question, right? So if you ask the wrong question, then it doesn't respond in the right way. And different models, these days probably all the models are pretty responsive to instructions, but if you, 2 years ago, not every model actually responds to your instructions, and also depend on how you instruct them. So, and the reason of the change is just that, these frontier labs, OpenAI, Anthropic, they train the models to be more responsive to your instructions. So they follow your order. And we're going to cover a little bit about image generation. So this is about how do you generate a realistic image from noise or from instructions. So this is the diffusion model. We're going to have one lecture on this. So this is also unsurprised because you don't have labels for these images. You just have a lot of realistic image, and then you can come up with a model such that you can generate more realistic images. So I think some of these data sets actually celebrity data sets. I don't know why they use celebrity, but apparently you can get a lot of celebrity data sets, and you can generate more images which looks like celebrities to some degree, right? With the right makeup, and the right style, so on and so forth. Very realistic. Anyway, so we can have one lecture on this. So, and then we're going to move on to reinforcement learning. So, this bullet is what I had 3 years ago, and I just add another bullet. Actually, I didn't make the form consistent. I probably should use training. Anyway, so I guess I think the typical way to think about reinforcement learning is that you are trying to this is a task, right? The task is that you want to make sequential decisions, right? You want to make decisions and sequential decisions. And the typical applications are like AlphaGo, like learning robots. Maybe actually it's kind of interesting to play this, right? So this is at iteration 10, the robots cannot really walk that much, and then eventually, you can, I think iteration 20 it doesn't do anything yet. And then at 80, I think it's walking a little bit. And, let me see. And at I remember for this example, now it's doing pretty well. And okay, and the point here is that this is the sequential decision task, because at any moment you have to decide what actions you take, right? So how do you move your arm? How do you move the leg, so on and so forth? So every time you have to take an action, and it's sequential because, what actions you take right now does affect your future, right? If you take the wrong move, then maybe you cannot recover, you're going to fall down, and then you can never move again. So there's a sequential dependency and there is action aspect. So that's the relatively kind of like traditional way to think about reinforcement learning. But I think these days people also use this as a tool to train models, especially when the model have stochastic decisions or stochastic kind of outputs in the middle. So probably a little bit, you have probably played with ChatGPT, right, or Cloud. So if you ask a question, right, it will generate a lot of like tokens, right, a lot of text, right, and some of the text actually not revealed to you because it's saying I'm thinking, right, but actually during the thinking process, it's kind of like generating a lot of like tokens, and all of these generation are stochastic sampling, right? So each time you generate a probability distribution and you sample from the probability distribution one of the words, right? And then you condition that word, or you give the word back to the model, and then you generate next word and you generate next word, so on and so forth. And each time is a stochastic sampling process. It's not a differentiable operation. So that's why to deal with this kind of like generation, you cannot really backprop through it easily. In some cases you can, but in some other cases you cannot. And you have to use reinforcement learning, which is a technique to deal with this kind of stochastic sampling steps in the models. I think that's and you can interpret each of the generation step as a decision. And it's a sequential decision because what you generate in the first word affects what you generate in the second word, so on and so forth.
So would you say that the first bullet point is how original RL was, and like the second is how we're using RL for LLM things?
Yeah, more or less, yes. Yeah, exactly. They are not fundamentally different. It's not like they are contradictory to each other. It's more like a slightly different kind of viewpoint in some sense. Yeah. Okay. I think another aspect of reinforcement learning is, I guess my automation is broken. So another aspect of the reinforcement learning is that it also allows you to collect data interactively. This is also very different from supervised learning and unsupervised learning. I'm not sure whether you're focused on, I didn't really emphasize those, right? In all of the supervised learning and unsupervised learning sections, at least traditionally, you are given a large data set. And then this is the data set you work with. And if you're given a bigger one, you're going to work with the bigger one. But your model don't generate more data. So the data set is given, right? So you can probably try to collect more and more, so on and so forth, right? That's on a different layer. But once you have the data, your model only sees those data, right? So but for reinforcement learning, it's kind of like a trial and error kind of like a type of algorithm where you iterate between data collection and training, right? So you try some strategy and collect feedbacks. For example, you can try how to walk and you fall down, and it falls down, right? So like there's still some data you collected, right? You collect some trajectory of data, a sequence of actions and observations for the trials, and those are new data for your training for the next round. So you can improve your performance based on the data you collected yourself, as opposed to just the given data. For example, another example is that so you can say automatic theorem proving. This is something that I kind of like work on quite a bit these days. So you're given some statements, you don't have the proofs. Right? You don't have the proofs, but first you generate some proofs yourself, and you try to verify and you select the correct ones. And those are the new training data. And now you have like some more training data because you generate some of them. And then you can train or reinforce the large language model on the correct proofs, with the hope that after you reinforce, then you can generate more correct proofs in the next round, and you get more data. And the next time you're going to train on more data, and then you keep going, and you have a bootstrapping kind of effect. And the same thing happens for robotics as well, right? You can collect more kind of trajectories, and then you train on the good trajectories. So and you can also use this for training large language models. The kind of the rough idea is that you have some inputs, which is, for example, a user prompt, and the large language model will generate a lot of text. And then you can have another module, either it's human reward or human reward model, or like kind of like another large language model. That's a separate discussion. But there's another module which given a text, you generate something called a reward. So basically, it's indicating whether this is a good text or not. And you can use this reward as a guidance for updating the large language model to generate better text in the next round. And the reason why we need to use reinforcement here is that it's needed because this whole process is not end-to-end differentiable in the most traditional sense, because the generation requires stochastic sampling. And that's why we're going to talk about how to deal with this case. I think the technique is called policy gradient, and you can use this and extend it. And some of the buzzwords is like ROVR, RO with verified reward, RO with human in the loop, ROHF human feedback, yes. And you can use this to train the long chain of thought. These are just buzzwords you don't have to understand. Anyway, so that's probably most of the lectures we're going to cover. And I think on the website we have a link to the syllabus. This is my internal version. I just take a screenshot, hoping that Cloud Code can make it more pretty, but it didn't really do the work, so I just have the ugly version. Yeah, anyway, but this is just summarizing what I have talked about. Yeah, I think we are going to have probably, what I didn't do is that there is another lecture we planned for ML system. So this is about how do you make the software and hardware more compatible. Actually, this is very important because if you can make your algorithm run 2x faster, you're going to save like billions of dollars for OpenAI, right? You don't even have to do it 2x faster. You can just only do 20% faster. It's going to be, because everything is so expensive, right? So, and even it's not like saving billions of dollars. It's actually, think about if I have algorithm is 2x faster than you, then it's 1 year for me and 2 years for you. And 1 year versus 2 years, that's just day and night, like for these days, right? Like, so that's why it's very important. And, we're going to talk a little bit about, we're trying to find a guest lecturer who can cover fairness and the social impact aspect of AI, which I think will be very important as well, just because AI is replacing so much jobs, and we have to think about the social impact of them. Yeah, I guess that's the overview for the course.